We would like to now introduce formally and with detail the definite integral. So what we wish to do is really define and compute pretty much at the same time areas. So if we have a function y equals f of x, we're going to just restrict our attention to continuous functions here. So we suppose it's continuous, it goes from a to b, and we look at the region enclosed between the graph and the x-axis from a to b. Then we define the area of this region to be the definite integral of f of x from a to b. So in this notation, the integral sign is really an elongated s, and a and b are called the limits of integration. Or you could call them also endpoints. F of x is called the integrand. And dx sometimes is referred to as the differential. We're going to see how this notation came to be. We should remember here that if a region has parts below the x-axis, then those parts count as negative. So you have minus for the parts below the x-axis plus for the parts above the x-axis. And that's why it's a good idea to say that the definite integral represents signed area between the graph and the x-axis. Now, the definite integral is also known as the Riemann integral from the 19th century mathematician Bernhard Riemann. So it's known as the Riemann integral. It's kind of interesting that the integral did exist long before the 19th century, but it was Riemann that actually gave it the proper definitions, and because of his contributions to shaping the theory of integration, it's now known as the Riemann integral. But it is true that integration in a certain way had been taken up in the antiquity by two mathematicians, the very famous Archimedes and Evdoxus, who established their method of exhaustion, which is a prototype for defining the definite integral. Here's pretty much what they considered. Let's say you want to compute an area of a curvilinear region. And basically what you can do is not compute it directly, but try to build rectangles that approximate that area and whose individual areas can be computed and summed up. And then you need to notice that as the rectangles become finer and finer, so let's say over this integral interval you had this rectangle, so the discrepancy is this one, but then you refine the way that the interval is divided, and all of a sudden you come up with this two rectangles that replace the previous one, and you see that now the discrepancy is smaller than it was before, and eventually it tends to zero. And by using this method, so you could do this from the inside or from the outside. And if you do it from the inside, then you really exhaust your region by using rectangles, hence the name method of exhaustion. And actually, Archimedes was able to give some very interesting computations of things that were done again hundreds of years later. So that was a theory that was way ahead of its time, and it might be easily considered as the first attempt toward a theory of limits and thus calculus. Now, we should also notice that what we described here, usually the lengths of these intervals are denoted by delta x. So pretty much each of these rectangles has area, some point which can be chosen to be on the left or on the right of the interval times delta x. The classical symbol for adding things together is the uppercase letter sigma. So this is sigma. And so in some sense, one can argue that the total area of the rectangles is a mathematical expression of this form. And now if we take the limit of this as delta x tends to 0, then we obtain, so the uppercase letter sigma gets replaced by an elongated s, the integrand becomes f of x, and you see this delta x is pretty much shaped into dx, and we get the integral from a to b of f of x dx. This is a very loose interpretation of how one could consider the transition from the actual tangible notation of areas of rectangles added together to the integral, to the symbol of the integral the way we know it. And of course, remember that this dx was something that was found in the Leibniz notation for the derivative of a function. So none of these things is a coincidence. They can be made to work out very harmoniously with each other. And this is the reason that this notation has been kept alive to this day. For derivatives, we have an alternative notation. For integrals, we don't really have any alternative notation, just some variations of the notation that we just saw. If you look at the history of mathematics, you will see that there were certainly different notations that were proposed. One, namely, that had a square in order to denote all these rectangles that are being built in order to approximate the area below the graph. So we have already seen the fundamental theorem of calculus, but in this lecture, we would like to simply ignore it and see what can be said without the fundamental theorem of calculus. And pretty much one of the things that we can give here is an estimate for the integral. So if you have a function y equals f of x on an interval a, b, and imagine now that you have a value which is smaller than all the outputs of f, let's say little m, and the value which is larger. Please note that little m and uppercase m could actually be the minimum and the maximum of the function over this interval. This could be actually the best choices, but they can also be any other numbers. Then this rectangle has area m times b minus a, and this is going to be less than or equal to the area of the between the graph and the x-axis, so to the integral from a to b of f of x dx, and that will be less than or equal to m times b minus a. Well, of course, if we wanted to sketch uppercase m times b minus a, it would have been this big area, and the integrals stand somewhere in between. So we would like to give some examples based on the definition of the integral. We would like to actually ask the question of what kind of integrals we would be able to compute right from the beginning. And besides integrals where obviously they're equal to 0 because the positive part and the negative part cancel with each other. So for example, the integral from a to b of sine x, I'm sorry, not from a to b, from negative pi to pi of sine x dx will be equal to 0, simply because the part on the right cancels with the part on the left. So as an example of an integral that could be computed in a direct way without any other knowledge is the integral of a function whose graph is a broken line. So let's take a look at this and imagine that this is 1, this is 3, and this is 5. Okay, and this is y equals f of x. So this could be described as a graph, as a function whose graph is the broken line from 0, 0 with vertices 0, 0, 1, 1, 3, 1, and 5, 0. And ask what is the integral from 0 to 5 of f of x dx. And pretty much here we go by the definition. Computing the corresponding areas is pretty straightforward. So this has area 1/2, and this has area 2, and this has area 1 by using the simple formula for the area of a right triangle, product of the lengths of the two right sides divided by 2. So the whole thing together will be found if we add these three numbers, and it's 3.5, or same thing as 7/2. So that would be the area, the integral of this function. And we should be able to find all integrals of functions that whose graphs are broken lines, like the ones that we just saw. As for the estimates, for example, again, without assuming the fundamental theorem of calculus, if somebody asked us if we can estimate the integral of the function e to the x from 0 to 1, then all we would need to do is notice that e to the x is an increasing function, hence it's greater than or equal to e to the 0, and it's less than or equal to e to the 1 for x between 0 and 1, which means that e to the x is between 1 and e. So these are the little m and the uppercase M that we saw in the previous page. And this would mean that the integral of e to the x dx from 0 to 1 is greater than or equal to 1 times 1 minus 0, which is the length of the interval, and it's less than or equal to e times 1 minus 0, which means that it's the integral between from 0 to 1 of e to the x dx is between the numbers e and 1. And these are pretty rough estimates, given the fact that e is about 2.71. So we just find out that this integral is somewhere between 1 and 2.7. The truth is that this integral is about 1.7 something. And of course, that is not conveyed by, that is a number which lies between 1 and 2.7, but the inequality is not that sharp. There's one more thing that we would like to add here, and this is that even though when we write the integral from a to b of f of x dx, one can assume here that a is less than b, we can actually extend the definition of the integral to the case that the number at the bottom is larger than the number on the top. So we can write that the integral from a to b of f of x dx is minus the integral from b to a of f of x dx if a is greater than b. And we can also define the integral from a to a of f of x dx to be 0. If we do so, if we allow ourselves these two extra definitions, then it turns out that the following equality is always true no matter what, as long as the corresponding integrals are defined. So the integral from a to b of f of x dx is the integral from a to c of f of x dx plus the integral from c to b of f of x dx. A simple question here would be, why exactly do we care about this? Are we going to encounter examples where the integral, the endpoints are going to be given in such an unusual way? And the answer is most probably no, but it will be needed for one of the things that we're going to say later. So here, when we say the integral from a to b, a could be less than b, a greater than b, c could be between a and b, c could be on the one side of a or on the side of a or on the side of b. It doesn't really matter. As long as the corresponding integrals are defined, we're going to have this relation. So all of these things allow us to prepare ourselves to understand a little how the integral works before we bring the fundamental theorem of calculus on stage, and everything, of course, will become different. That is going to be our next call pretty much. But this completes our elementary introduction to the theory of integration. Thanks for watching.